Hi, welcome to Beginning Engineers. Today I'm going to be doing something a little bit different for me. I'm going to be taking a topic that I've already done a video on, and I'm now making a video going deeper into that topic. Of course, I'm still going to keep the concepts at a high level and walk through more complex ideas slowly because, again, this is Beginning Engineers. So hopefully you're like me and you've seen a bunch of quantum computing videos already, so you understand some of the basics. If not, my last video, and I'll put a link in the description if I can remember, went into quantum computing from a high basic level, as do most other videos you can find on YouTube. But this video goes a level deeper. So at the heart of a quantum computer, you have the qubit, the quantum bit. That is what makes quantum computing so amazing. But what actually is a qubit? So physically, what is a qubit made out of? They can be made out of different things, depending on how you build your quantum computer. They can be made out of photons, which are elementary particles in the electromagnetic field, like light, for example. They can be made out of something called a coherent state of light. A coherent state is an eigenstate of the annihilation operator in the Heisenberg picture. Okay, so if you're not a physics major and you're like me, that sentence makes no sense to you. So let's break that down a little bit. You have something called the uncertainty principle, which says with things like particles, you cannot know both the momentum and position of a particle at the same time. You can only know one or the other. So because of this, statements about both the position and momentum of particles can only assign a probability that the position or momentum will have some numerical value. So you look at both things and you assign a probability to each. Remember that concept because that comes back later. This uncertainty principle seems very strange to us who live in the physical big world, the world outside of super tiny things. You walk around and you see objects. You know where they're at, you can see their position, and you know their momentum. If you see somebody standing still, you know both their position and their momentum. But in the world of the super small, you can only know one or the other. This is the uncertainty principle. So if you know an electron's momentum, you will not know its position. If you observe an electron and know its position, you don't know its momentum. Once you make that measurement and determine either position or momentum, the wave function, that is, all probabilities of that electron, have been collapsed, meaning you now know something. It is no longer in a superposition. This collapse can be referred to as an eigenstate of position. The electron's state is an eigenstate of position, meaning that its position has become a known value. Coherent states are good for measurability. So if you want to measure something, you need a coherent state. You need to know something about what it is you are measuring, like its position. It's good that you can measure it because it will be able to produce a value. If you're not observing either position or momentum, you don't have any definite values, but a coherent state gives you one. So physicists and engineers are able to know the position or momentum for light. They can get a coherent state of it. Also, qubits can be made out of electrons or nuclei. They can be made out of something called optical lattices, which are crystals made of light that can be used to trap atoms at very low temperatures, creating a workshop in which to pore over and tinker with fundamental properties of matter. Qubits can be made from Josephson junctions. A Josephson junction is made by sandwiching a thin layer of a non-superconducting material between two layers of a material that is superconducting. So it's like a superconducting and non-superconducting sandwich. Josephson junctions are good candidates for qubits because they have low dissipation inherent to the superconductors they're made of. That low dissipation means that there can be long coherence times. So long times that you can view the collapsed state. Also, Josephson junctions are easy to scale up in production, at least compared to other types of qubits, which is good because if we want practical quantum computers, we need more than just 3 or 4 qubits. You can make qubits out of a single quantum dot or singularly charged quantum dot pair. So what is a quantum dot? Quantum dots are man-made nanoscale crystals that can transport electrons. When UV light hits the semiconducting nanoparticles, they can emit light of various colors. These artificial semiconductor nanoparticles have already found applications in things like composites, solar cells, and fluorescent biological labels, so they are already in use, which makes them a good candidate for qubits. Okay, I'm not expecting you to be a master physicist and understand what all these qubits are made of and exactly how they function. But at this point, if you're like me, maybe you noticed a trend. Qubits must be made from really tiny things that display superposition and can ultimately be collapsed into an eigenstate for analysis to produce a result. A computer calculation, for example. Traditional silicon chips with their logic gates do not exist in superposition or have the uncertainty principle needed. So all these qubits are made from super tiny things. Electrons, light, things like that are super small and very touchy. So you have to be very careful when using these things. So how do these qubits actually work together to perform calculations? In my first quantum computing video, I talked about traditional bits being used with logic gates. 2 bits being used with 2 gates to produce an outcome. Qubits operate on the same principle. They have quantum gates, which are more complicated to understand, but it's the same basic idea. The qubits actually work together, though, using something called entanglement. Quantum entanglement is a physical phenomenon that occurs when a pair or group of particles is generated, interact, or share spatial proximity in a way such that the quantum state of each particle of the pair or group cannot be described independently of the state of the others, even if the particles are separated by a large distance. Quantum entanglement is at the heart of quantum mechanics, and it's not something that exists with classical mechanics. It's part of what makes quantum mechanics so strange. To understand this in the real world, imagine that it is the future, and you and your friend entangle 2 particles. Your friend then takes his particle to a Mars colony, and you are still on Earth. If you observe your particle and collapse it, so it becomes an eigenstate, you know its spin, let's say, you know what direction your particle is spinning, you will immediately know that your friend's particle on Mars, so really far away, you'll immediately know the direction it is spinning. You have collapsed the entire wave function. Entangled particles act like a whole unit. So if you observe one, you know something about the other, regardless of how far apart they are. Einstein called this spooky action at a distance, because it can be a very large distance, yet you immediately know something about the other particle based on your particle. It's very strange, very spooky. You can describe the state of the whole system by summing its individual parts, which is good because that is similar to how traditional bits work. Okay, let's use a really oversimplified example so that you understand how entanglement and qubits are used for a calculation, and what makes quantum computing so powerful. So let's have a regular computer and a quantum computer compete to calculate the numbers 0, 1, and 2 using just 2 bits, or 2 qubits. In binary, 0 is 0, 0, 1 is 0, 1, and 2 is 1, 0, and that takes 2 bits. The bit 1 represents on, and the bit 0 represents off in binary, because again, binary only has 1 and zeros. A traditional computer would need 6 bits to calculate all 3 of these possible answers. You need 2 bits for 0, 0, 2 bits for 0, 1, and 2 bits for 1, 0. That is with a traditional computer. So 6 bits are needed for a traditional computer. For a quantum computer, though, because those 2 qubits exist in superposition, where either qubit is 0 or 1 at the same time until it is collapsed, the qubits can be collapsed into either 0, 0, 0, 1, or 1, 0 as needed. So it's like all 3 possibilities exist at once. So if we know the answer, We just don't know the value, but we can compare against the answer to see what is correct. With a traditional computer, you would have to compare all three possibilities. You would need 6 bits. With a quantum computer, if we know just a little bit about the answer without knowing the exact setup of the answer, so we don't know the value, but we can check against it somehow, we can collapse our 2 qubits to be the answer that meets the criteria to be correct. So we can collapse just 2 qubits into the correct answer. We don't have to go through all 3 combinations. And through entanglement, we know the output of the entire system, and we know something about each piece, each qubit. That efficiency you get with just 2 qubits scales with every single qubit you add, so that with 10 qubits, you're replicating 1,000 regular bits, roughly. And then by the time you reach 20 qubits, you're replicating 1,000,000 regular bits with just 20 qubits. So you can imagine how powerful a quantum computer would be with 30 qubits, 40 qubits, 50 or more qubits. But how do you physically entangle the qubits? Okay, well, just like the physical properties of qubits, this gets pretty technical quick, but we can still look at a few methods from a very high level. Quantum systems can become entangled through various types of interactions. For some ways in which entanglement may be achieved for experimental purposes, see the below section on methods. Entanglement is broken when the entangled particles decohere through interactions with the environment. For example, when a measurement is made. That collapses the wave function. It uses the word decohere, and decoherence is a huge issue in quantum computing. It's also known as noise. These qubits are so particular that they are very easy to collapse or mess up. You can get errors, so you have to be very careful with how you entangle and how you collapse the wave functions, the qubits. You can entangle via spontaneous parametric down conversion. This is when a nonlinear crystal is used to split photon beams into pairs of photons, so particles of light in this case, that, in accordance with the law of conservation of energy and law of conservation of momentum, have combined energies and momenta equal to the energy and momentum of the original photon and crystal lattice. So you split a photon into 2 smaller pieces that together will have the same energy and same momentum that the original photon had before it was split. You can entangle using something called a fiber coupler, and from my research from a high level, this seems similar to spontaneous parametric down conversion. You can entangle by using photons emitted from decay cascade of the biexciton in a quantum dot. So this is another sentence that is super complex, but let's break it down a little bit. Decay here refers to particle decay. Particle decay is the spontaneous process of one unstable subatomic particle transforming into multiple other particles. The particles created in this process, the final state, must each be less massive than the original, although the total invariant mass of the system must be conserved. So the pieces again add up to the whole. And you are probably familiar with the word decay. It's kind of like things falling apart. This happens on a particle level too. A particle will decay into multiple smaller particles. In condensed matter physics, biexcitons are created from 2 free excitons. An exciton is a bound state of an electron and an electron hole, which are attracted to each other. And an electron hole is the lack of an electron at a position where one could exist. So see that diagram on the right? It has an oval around the electron hole and the electron. Together, those are an exciton. So in summary, qubits are made from extremely tiny things, like electrons or photons, things that small. They are entangled by splitting beams of light through the natural cascade decay of particles. Other methods like that often create smaller particles that sum to be the whole particle that was split before. The reason I went into such depth about what qubits are and how to entangle them is for you to understand the complexity of a quantum computer. It is really hard to make and control these things, and we are only at the early phases of quantum computing. But there are many comparisons that can be made to traditional computers. Just like traditional computers started out filling up entire rooms with a very low number of bits, quantum computing is still in its infancy. And like regular computers, quantum computers use gates, quantum gates. But because qubits exist in superpositions, we need matrices to understand quantum gates. Think about it in terms of bits. A qubit can be 1 or 0, but you don't know until you collapse the superposition. To capture both those possibilities, you need two values, but two values contained inside a single qubit. That's why matrices are used. They capture the different possibilities of the qubits. So let's have a quick review of matrices. Quantum logic gates are represented by unitary matrices. The number of qubits in the input and output of the gate must be equal. A gate which acts on n qubits is represented by a 2 to the power of n times 2 to the power of n unitary matrix. The quantum states that the gate acts upon are vectors in 2n complex dimensions. The base vectors are the possible outcomes if measured, and a quantum state is a linear combination of these outcomes. The most common quantum gates operate on spaces of 1 or 2 qubits, just like the common classical logic gates operate on 1 or 2 bits. Okay, so that was a lot to unpack. We're going to start more basic with matrices and work our way up to understand a unitary matrix. In that definition, the term vector was used with matrices. For these purposes, a vector is a quantity having direction as well as magnitude, especially as determining the position of one point in space relative to another. This is as opposed to scalar quantities that only have magnitude. 30 feet, that's scalar. It's a length that has a value, 30 feet, but you don't know what direction the 30 feet are going in. So a matrix, again, has a width and a length. It has rows and it has columns. In the picture on this slide, I have a 2 by 2 matrix that has 4, 0, 1, and -9 inside of it. To multiply a matrix by a single number is pretty straightforward. In this example, we are multiplying by 2. You take the 2 and multiply it by each number inside the matrix, so that the resulting matrix is the same as the original matrix, but with each value being multiplied by 2. So the resulting matrix in this example is 8, 0, 2, -18. It's the original matrix times 2, each value times 2. Multiplying one matrix by another adds another level of complication. Before we jump straight into it, make sure that you think about a matrix in terms of rows and columns. So in the top right graphic, they are labeled R1 and R2 for row 1 and row 2, and C1 and C2 for column 1 and column 2. And one great way to think about it is to think of each row and each column as its own tuple. And if you are not highly involved with mathematics or developing, you might not have heard the word tuple before, but really just think about a tuple like a list. If we have two tuples, 3, 1, and 2, 4, how would we multiply those tuples together? Well, you might have guessed it. We multiply the first value in the first tuple by the first value in the second tuple, and then add that sum to the second value in the first tuple times the second value in the second tuple. So in this case, 3 times 2 plus 1 times 4. So 6 plus 4, 10. So you take this idea of multiplying tuples and then look at a matrix and look at each row as a tuple and each column as a tuple. So then if you're multiplying matrix A by matrix B, the resulting matrix, matrix C, each value within that matrix can be considered a tuple from one matrix times a tuple from another matrix. So in matrix A, the tuples are the two rows. In matrix B, the tuples are each column, so that the top left value in matrix C is row A1 times column B1. So you multiply those two tuples together, 1 and 7 times 3 and 5. So 1 times 3 is 3, plus 7 times 5, which is 35. So 3 plus 35 is 38. And based on that image I have on the right side, the third image down, you can see how each row times each column between your two tables gives you the resulting matrix C, which is 38, 17, 26, and 14. If you're like me, this isn't super intuitive at first, but look at matrix C, the third image down on the right, and realize that every time you change rows in that matrix, you're changing the row from matrix A that you're multiplying by. Every time you change columns, you're changing the column of matrix B you are multiplying by. So those do line up pretty well. So if you take a minute to really look at the images and understand which tuples, which rows and columns you're multiplying, I think it will click more. With matrices, you can do something called transposing. A transpose matrix is where you take your original matrix and change the rows and the columns to get your transpose matrix. If you are ever doing matrix math and you see a superscript t, kind of how numbers will be raised to a power and that number is smaller to the top right of that number, if you see a t like that on a matrix, that means you're going to take the transpose of that matrix, like my first image on the top right shows. There is also something called a conjugate matrix, but to understand a conjugate matrix, we first need to know what complex numbers are. A complex number is a number that can be expressed in the form a plus bi, where a and b are real numbers, and the I is the solution to the equation x squared equals -1. The value of x is I. It's called an imaginary number, if you remember that from algebra. So a and b are real, I is imaginary. Together, they are a complex number. Mathematicians think that I being called imaginary is a bad name, because these numbers are very much real in the natural scientific world. For example, we are talking about them now, and they help explain quantum computing, which is a real thing that is happening currently. So why are complex numbers important for quantum computing? For starters, let's think about a traditional computer. A bit is either 0 or 1. There is no probability. It's going to be one of those two choices. It is either known to be 0 or it's known to be 1. But a qubit is inherently probabilistic, meaning that two identical qubits may have different values once measured. Quantum computing, you have to think about in terms of probabilities. When talking about the probabilistic nature of measuring qubits, two numbers are used: the absolute value of alpha squared, which is the probability that the qubit will be measured as 0, and the absolute value of beta squared, the probability that the qubit will be measured as 1. These are both probabilities. But once the qubit is measured, we know what it is. So you can think about the internal state of a qubit as a probability amplitude, alpha and beta. These are complex numbers, which define a superposition between 0 and 1, because the qubit exists between 0 and 1 until we observe it and collapse the superposition. So qubits can be represented by complex numbers. And if we have complex numbers in a matrix, that matrix is a complex matrix, like matrix A in the top right. The conjugate matrix, A bar, so the second image on the right, looks very similar, but with one noticeable difference. The conjugate of a complex number has the same real number component and imaginary component with the same magnitude, but opposite sign. So instead of 1 plus I, it's 1 minus I. Instead of 1 plus 2i, it's 1 minus 2i. So see how the real number stays the exact same, and the imaginary number has the same magnitude, but the sign is different? Plus 2i becomes minus 2i. The 1 stays the same. That is what a conjugate is. But why is it important? What is the benefit of a conjugate number? Well, if you take a complex number and then multiply it by its conjugate, the imaginary parts cancel out, so that you are left with a completely real number. The conjugate of 1 plus 2i is 1 minus 2i. If we multiply those together, we get 1 squared minus 2i plus 2i minus 4i squared. The minus 2i and plus 2i cancel out. The 4i squared, well, I squared we know is negative 1, so 4 times negative 1 is negative 4, so minus a negative 4 is plus 4. So we multiply 1 plus 2i. If we multiply that by its conjugate, we end up getting 5, because 1 plus 4 is 5. To turn a matrix into its conjugate matrix, you just take each complex number inside the matrix and take the conjugate of that complex number. So you can see in my top two images, A becomes A bar. You can have a matrix and take both the conjugate and transpose of that matrix. This is also called the Hermitian transpose. So if you see a matrix labeled with the superscript H, that stands for Hermitian transpose. Sometimes you'll see a symbol that looks like a little dagger, and it will be called a dagger. That also means the conjugate transpose. So quantum gates are represented by unitary matrices. A unitary matrix is a matrix that when multiplied by its conjugate transpose, so what we just went over, results in an identity matrix. And an identity matrix is a matrix where the diagonal is all ones, but every other value in the matrix is all 0. Nothing but zeros. Unitary matrices preserve the magnitude of a vector under rotation or reflection. And that's good. That means using our quantum gates, we still have the same magnitude for our qubits, regardless of rotation. We introduce and define the symbol alpha with that straight line and what looks like a greater than sign to represent a quantum state, kind of like I touched on earlier with the absolute value of alpha squared. These shapes all together are called a ket, K-E-T, or a ket vector. It is an abstract entity and serves to describe the state of the quantum system. We say that a physical system is in a quantum state alpha, where alpha represents some physical quantity, such as momentum, spin, etc., when represented by the ket. So when looking at qubits, the value 0 in a qubit is represented by the ket 0, which represents a 2x1 matrix with 1 on top and 0 on the bottom. The value 1 in a qubit is represented by the ket 1, which represents a 2x1 matrix with 0 on top and 1 on the bottom. In order to represent an entire qubit, so not just a qubit in state 0 or state 1, we use the vector below, which takes into account the complex probability amplitude of the qubit, the probability of measuring A0 or A1. So it's the ket alpha, which represents the kets 0 plus 1. The gates of a traditional computer take inputs and convert them to outputs. A quantum gate does the same thing. In my images on the right, you can see an example of one type of quantum gate, a poly X gate, that converts a 1 ket to a 0 ket. And if you look on the bottom part of the image, you see how this is done, or represented, with matrix multiplication. A poly X gate can be represented by a 2x2 matrix with the values 0, 1 and 1, 0. If we multiply a 1 ket by that matrix, the resulting values are 1, 0, which is a 0 ket. This matrix, the poly X gate, flips the qubit. What are quantum logic gates made out of in the real world? Well, they're implemented via ions and lasers in one scenario I found with my research. In a lower energy state, the ion represented a 0. In a higher energy state, it represented a 1. The ion's internal energy was the first qubit. The team created a second quantum bit with the atom's external motion. 0 represented less motion, and 1 represented a greater amount of motion. The research group then entangled the ion's internal energy with its overall motion. This is the quantum version of a controlled NOT gate, a C-NOT gate. In their gate, the ion's energy of motion serves the control bit. If it is a 1, then it causes the ion's internal energy state to flip. In a C-NOT gate, if your control bit is 1, It causes the other bit to flip, to change its value. Using lasers, the researchers could also cause the ion's internal energy state to go into a superposition of 0 and 1, putting the ion's motion into a superposition of 0 and 1 as well. This allows the gate to process multiple possibilities simultaneously, unlike ordinary logic gates, so the gate can be considered both yes and no at the same time. Again, that's superposition. It's why quantum computing is so powerful. Because this video is already so long, I'm going to go through our next and final topic very fast: quantum error correction. Because of the high sensitivity of quantum computing setups, intensive efforts for error correction are needed. Right now, quantum computing has a big problem called decoherence, which is also known as noise. Decoherence can cause quantum superpositions to collapse incorrectly, giving the wrong answer. But with error correction, you help prevent this. One example of quantum error correction, QEC, is called 3-bit code. An example of this is that you have someone sending a message to someone else using qubits. By using 3 additional qubits, you are able to help ensure that the right information gets transmitted. You are left with probabilities about what is right and what is wrong, and by entangling your bits with 3 additional bits, you can help rule out incorrect information. Basically, by entangling different bits and creating CNOT gates, where if one qubit is a 1, it flips the other qubit, you go through this process with your 3 bits, and eventually, what you are left with has the highest probability of all possibilities for being correct. If I had more time, I would go more into QEC, but you can pause on each of the slides and follow the example I wrote up. Also, if I had more time for this video, I would have liked to go into a few other topics of note for quantum computing, and maybe in a future video I will go into these subjects more. The first is encryption. Because quantum computers have the potential to simulate so many different values at once, a sufficiently advanced quantum computer could easily break the 3 common methods used for encryption today. Because encryption today relies on difficult mathematics, where guessing the correct combination for someone's encryption would take so many different combinations you would have to try, it would take way too much time. But a quantum computer could figure that math out very quickly. If I had more time, I would have gone into the physical setup of quantum computers, because they look nothing like classic computers. If you remember the image from my first slide, that is what a quantum computer looks like. They are very cylindrical, but also they have very interesting physical properties. They must be kept extremely cold in order to work properly. The quantum processor, so a quantum computer's equivalent to the CPU, must be protected from all types of potential noise, like electromagnetic radiation. There is something called the superposition principle, which is a really interesting concept to go into, that says you can add together different states to get a final state. So my images on this slide show that in practice. If you add together a wheel's rotation, and you add that to a wheel's linear motion, putting them together means you have a rolling wheel, but those are 2 different states added together: the superposition of rotation and linear motion. And finally, I would have talked about some existing quantum computers, how powerful they are, and what the future holds. But all in all, this video took the basics of quantum computing and went to the next level, giving examples of some of the math and physics behind quantum computing. If you enjoyed this video, feel free to like it and subscribe to my channel. I tried to come out with an engineering video about once a month. Thanks for watching, and have a nice day.